All right, everybody, let's go ahead and get started here. So yeah, today I'm essentially doing what I was supposed to be doing on Wednesday's class, where I'm gonna both answer a bunch of your questions on things and also just help you guys do some review. Unlike the other sections, I guess there are kind of fewer tips I can give in general for this exam. I guess one thing that you definitely need to remember would be to draw graphs for the polar area problems. That would be definitely something that I would remember right there. Let's see, is there anything else that's like a good hint in general? I don't really think so. I think ultimately it kind of just comes down to solving the problems, and the practice exams and old exams definitely have a lot of good practice. So why don't we just spend our time going over this? So that'd be the most productive use of the time. All right, let's see here. Oh, Hayden's asking about exam accommodations. Yeah, so if you click the same link that you used before, so if you look at one of the old announcements, you can also get exam accommodations if you still need them. All right, let's see. Jessica is starting things off here in the chat. Can we go over number 10 on the third practice exam? Absolutely. Let's see, let me get that pulled up here. All right, number 11. Okay, which of the following sets of parametric equations forms a circle? I'm actually going to screen share my internet here because I don't think there's a lot of writing for this. I think it's just looking at things. So let me share this. All right. So can everyone see my screen? Can everyone see the internet here? Is this okay?
Oh wait, that's number 11. I asked about number 10.
Oh, I'm sorry. I was looking at Natalie's question, which was number 11. So number 10. Yeah, this one. Well, since I'm here, I guess I'll do number 11 now, and then I'll do number 10 afterwards. Sorry about that.
Okay.
Okay, so number 11 here. Which of the following sets of parametric equations form a circle? Now, remember, in order to form a circle with parametric equations, you need to have one of x and y be sine, and the other one be cosine, and then you need to have the same thing on the inside of both of them. Let's go through this and see which one of these might be a circle. So the first one we have here is x is sine and y is sine. Well, we need one of them to be cosine, so this is definitely not going to be a circle. Let's see, here we have x is secant and y is cosecant. And I mean, while these do have to do with sine and cosine, like this is cosine, this has to do with sine, this isn't quite the way we need it. We need the cosine and sine to be in the numerator, not the denominator. So this won't work as well. Here, x of t, we have cosine squared, and y of t, we have sine squared right here. This one might seem tempting because this kind of looks like the Pythagorean theorem, but alas, you need just cosine or sine in order for this to work. So this one will also not be a circle. This one right here literally is the Pythagorean theorem. If we simplify this fourth one here, this would just be 1, and then y would be t, but that's not a circle. That's actually a vertical line at the point x equals 1. So that's definitely not a circle. So I guess by process of elimination, the last one has to be, but let's see why it's a circle. Let's see, we have sine for one of them, cosine for the other, and they have the same inside. Now, even though that inside is weird, even though it's natural log, it still counts as a circle. It's just that as you draw it, or if you imagine it as a particle, it will move around the circle in a weird way, but it will still go all the way around the circle. So it's the last one here that ends up being our circle from this list. And remember, the key features are one has to have sine, one has to have cosine, and then they have to have the same inside. And yeah, here's a question from Cindy. Does it matter if x or y is sine? No, as long as one of them is sine and the other one's cosine. Switching which one it is just affects where you start on the circle. But it'll still be a circle. All right, great. So we did that one. So let's go take a look at this one. Number 10 here. Let me write this down and I'll switch back to my other camera. Exam 3. Why doesn't the square work again? Because let's say we wanted to put this into the circle equation, right? We need x squared plus y squared to be 1. But if we use the squares here, that'd be cosine to the fourth plus sine to the fourth equals 1. And while that might seem like it's true, it's actually not true. The Pythagorean theorem does not work for sine to the fourth and cosine. All right, let me flip back over to my overhead. All right, great. So for the 10th problem on practice exam 3, which is our next problem here, we want to find the 50th derivative at 0 for the function, this is our function here, x squared e to the 2x. Now, every year, without fail, whenever this is on the exam, someone tries to take like 50 or 100 derivatives, whatever insane number of derivatives it is. And I strongly urge you not to do that. That is not a good strategy for doing this. The strategy we're going to use instead is we're going to use the power series coefficient formula. So remember, if we want to get a Taylor or Maclaurin series for a function, what we do to get the coefficients is we look at the nth derivative at the center, and it looks like 0 is going to be our center here, and then we divide by n factorial. Now, usually when we're making our Taylor or Maclaurin series, we usually use the formula this way, where we put in the derivative of the n factorial, and that gives us the coefficient. But there's no reason why we can't use this the other way around. There's no reason why we can't take the coefficient, multiply it by n factorial, and then get a derivative here. Yeah, there's no reason why we can't do that. All right, so in this case, since we want 50, the 50th derivative, we have a sub 50 times 50 factorial is the 50th derivative of 0. All right, so 50 factorial is something we can have as part of our answer. It's just a number. So we really just need to figure out what a50 is. If we have a Maclaurin series for this function, we just look at the number that's next to x to the 50th, and that will be our a50. All right, well, that means we need to figure out a Maclaurin series for this. Now, the closest series that you would have on your formula sheet to this would be e to the x, which is the sum from n equals 0 to infinity of x to the n divided by n factorial here. All right, now we need to get e to the 2x, so that's going to require us to substitute in 2x here. All right. 2 to the n, x to the n, if we do that. And then finally, we need to multiply this by an x squared in order to get the function we want. We'll multiply both sides by x squared here. And whenever we're doing anything with power series, we want to get all the powers of x's in one place. So I'm going to move this x squared within the series and combine it with this. So this is the sum from 0 to infinity, 2 to the n, x to the n plus 2 divided by n factorial. And remember, we can move anything in and out of the sigma if it does not have an n. So there we go. So this is our Maclaurin series for that function. Now remember, our goal is to find a50, which is the coefficient, so the stuff not including x, that's next to x to the 50th. So that means that we need to see which n value will make this formula give us 50. And I think this one's pretty clear to see which n value would I plug in there to get x to the 50th for this one. That's right. Yeah, it's going to be 48 because we have something plus 2 is 50. That means the n that we're going to be using to get our coefficient will be 48. Now, this is a bit of a confusing part because we have 50 right here, but we're plugging in 48. Reason being is that this n is not the same thing as the n that you're using in the series. These n's and this n is totally different. I am going to plug this into here, and that means that my a50, or the thing next to x to the 50th, which happens at n equals 48, will be 2 to the 48th divided by 48 factorial. So we can finish things off by plugging that in here, and we see that our derivative is 2 to the 48th times 50 factorial divided by 48 factorial. That is going to be our derivative here. I don't know about you guys, they definitely wouldn't want to take 50 derivatives manually here. That would not be fun. So anyways, this is our derivative here. Marion asks, if it were e to the x squared, how would it change? Would it be x to the 2n? You're absolutely right. So rather than putting 2x in for the substitution here, If I have an x squared in here, I would substitute that in, and it'd be x to the 2n. And then I would have 2n equals 50, so the n I would plug in for that problem would be 25 to get my x to the 2n.
So for these, are we just setting whatever like x, like the power is to 50, basically? Like,
Yeah, whatever derivative you want, you set your power of x equal to that. Absolutely.
okay, and then you ignore the other stuff for that part, and then you like put it back.
Yeah, you take whatever n it is, and then you put it in here to get your coefficient.
Okay, thank you.
All right. Let's scroll back up here. Definitely have some more questions. Oh, I'm sorry, I skipped over Daniel's question as well. I don't know what I was doing. Daniel wants to go over number 1 on practice exam 3. And this one wants us to find, so this exam 3, number 1. I think this one, if I'm not mistaken, wants us to find the IOC for this power series. The sum from 0 to infinity of x, but it's raised to the n factorial. So this is definitely something a little bit strange. So we want to find the interval of convergence for this series. Now remember, every series converges at least one point, and this one will converge at x equals 0 for sure. But any other number, we'll see what's going to happen. All right, now as tempting as it is to do the ratio test here, I usually say use the ratio test whenever you have factorials. This is one exception here. I'm actually going to use the root test for this for a reason we'll be seeing in a second. So I'm going to use the root test to get my IOC. Now remember, root or ratio can give you IOC, so this is also fine. So for the root test, I compute a limit, and that limit is the limit as n goes to infinity of the absolute value of this stuff, all raised to the 1 over n power. Okay, so and remember, whatever I get from my root test, it needs to be less than 1 in order for it to work. All right, so let's see here. So I'm going to move the absolute value in here. You can move powers outside of the absolute value. So I have the limit as n goes to infinity of absolute value of x. Now, if I combine the n factorial and the 1 over n power, those powers combine by multiplication. If you have power to the power, they multiply. Let me ask you guys this. What's n factorial times 1 over n equal to? What will that simplify to be? So we have 1, n minus 1 factorial. That's right. The n minus 1 factorials have it, because remember, n factorial is n times n minus 1 factorial. So if I divide both sides by n here, those will go away. So I really just end up with n minus 1 factorial. All right, now if we look at this, remember, whatever we get from this limit needs to be less than 1, right? So let me ask you guys this. If I plug in an x value that's bigger than 1 into here, what's going to happen with that limit? Like let's say I plug in like x equals 2, and I raise that to the n minus 1 factorial, and n's going to infinity. Yeah, that's definitely going to be infinity. That's going to diverge for sure. However, if I put 1/2 in here, for example, or something that has absolute value less than 1, then what I'm doing is I'm multiplying a bunch of numbers together, and there's going to be a lot of them because factorials are big. I'm going to multiply a bunch of numbers together that are less than 1 and are consistently valued less than 1. So which x values do you think will make this limit converge, or this limit exist, based on that reasoning? -1 to 1, that's right. So if I put something in here that has absolute value less than 1, we're multiplying a bunch of those numbers together, so that will decrease towards 0, and 0 is less than 1. All right, so we know that our interval of convergence is at least -1 to 1. But of course, we always have the predicament, what happens if it's exactly -1 or 1? Can we do those? Well, that means we just need to put this in and test it manually. Let's check x equals 1 here. That's 0 to infinity. Well, if I have 1 to n factorial, it doesn't matter how huge that power is, 1 to n factorial is going to be just 1. This is the sum from 0 to infinity of 1, and obviously this is going to diverge here. All right, and then let's check x equals -1. This one's a little bit different. We have n equals 0 to infinity, of -1 to the n factorial. Okay, now how is this going to work? This one's actually a little bit strange. So if I plug in n equals 0 and n equals 1, n factorial for both of those will be 1. So I have -1 minus 1 for the n equals 0 and n equals 1. And then I have n equals 2 to infinity of this. Now the thing is, any factorial from 2 onwards is going to be what? An odd number or an even number? Any factorial from 2 onwards is going to be what? Odd or even? That's right, it's going to be even. Reason being is that any factorial from 2 onwards will include multiplication by 2. So for example, 4 factorial will be 4 times 3 times 2 times 1. So any number once we start getting to 2 will be even here, and -1 to an even power will just be 1. So this is -2 plus the sum from 2 to infinity of 1. And once again, this is going to go off to infinity. This one was a little bit trickier to see, but this one ends up diverging as well. So we end up getting that our interval of convergence is -1 to 1, not including either of the endpoints. Marion has a question here. Why isn't it x equals 0 since it's infinity? Well, for example, 1/2, if we look at the limit as n goes to infinity of something like 1/2 to the n, and this is going to infinity, you're multiplying a number less than 1 by itself a bunch of times. So like a half times a half is a quarter, and then times another 1/2 is going to be 1/8, times another half is a 16th. So you see that's how it's decreasing to 0 as we go through that. So that means that any number in between -1 and 1 that has absolute value less than 1 will work for this. It's possible to prove divergence through the AST. That's actually what we, oh wait, through the alternating series test? Well, remember, we don't ever prove divergence through the alternating series test. We usually prove divergence through the test for divergence. And that's exactly what we did through these. Test for divergence and test for divergence right there. Really, we want to use rooted ratio test to get the bulk of our interval for intervals of convergence. All right.
Manly, could you explain how you got the interval again?
Yeah, so we're trying to figure out which x values, if we plug it into this limit here, will give us a result less than 1. So we discussed how if we plug in something that has absolute value bigger than 1, like maybe 2, we're multiplying a bunch of 2's together, and that'll just keep getting bigger towards infinity. So there's no way that's going to be less than 1. But on the other hand, if we plug in a number that's absolute value less than 1, like say 1/2, if I keep multiplying those together, that limit's going to go to 0, which is less than 1. So anything that has absolute value less than 1, which is in this interval right here, those will all go to 0, and so they'll satisfy the root test. That's why it's this in it.
Oh, I'm still a little confused. Can you write it down, like an example?
Yeah, sure. So for example, let's say I decide to plug in like x equals 1/2. So if I plug x equals 1/2 in here, then I have the limit as n goes to infinity of 1/2 to the n minus 1 factorial. Now this n minus 1 factorial, this is getting really big, right? So I'm effectively multiplying a bunch of 1/2s together, because that's what exponentiation does. It's multiplying the same number by itself a bunch of times. So this is equal to 1/2 times 1/2 times 1/2 times 1/2. And every time I multiply a half together, it gets smaller and smaller every time. So this limit's going to equal 0. And remember, whatever we get for our limit here, it needs to be less than 1. So if we got 0, this would be okay. But then the opposite would happen if I did something like x equals 2, which is not in here. That's going to keep getting bigger and bigger if I multiply it by itself. So that will not be less than 1 in the long run.
Okay, thank you.
Yeah, no problem. All right, let's go back here. Let's see. So we did 1 on practice exam 3. We did 10. We did 11. Can we go over 3 on assignment 20? Carly asks. Yeah, absolutely.
Oh, Professor Manley, I have a question about the practice test in general.
Okay.
So the practice test, at least the one that you gave to us, I found it a lot easier than like the previous exams. So what would you say the difficulty of our exam is more aligned with?
It should be relatively close to this practice exam. So if you feel like you're doing well on that, then that's a good sign for
Okay. And on one of the questions you gave us, the m is equal to 24. Is that something that we're gonna have to solve for on the test, like m, or
If
would you
it's
give it to
something
us?
that's like really straightforward, like your m is just bigger than sine, so you could just pick it to be 1, I won't tell you. But if it's something really complicated, I'll give it to you.
Okay, perfect. Thank you.
All right, anyways, let's do 3 on 20 here. So this one, this is an interesting problem. Homework 20, number 3. Find the area enclosed within the curve r squared is cosine of 2 theta. So that is our goal for the next problem right here. All right, so let's see here. Let's go up. Oh yeah, so I think I see her in the chat. So some people were talking about like if you differentiate a series, then you need to move the index up to n equals 1. You could go either way on that. So if you plug in the n equals 0 in, like let's look at an example. Sorry, I'm going to do this example before I talk about this one because this is something a lot of people have been asking. So if let's say I have 1 over 1 minus x, which is the sum from 0 to infinity of x to the n. Now let's say I wanted to differentiate both sides to get a series for a new function. So if I take the derivative of those sides here, then the derivative of this is going to be 1 over 1 minus x squared if I do the chain rule and all. And then the derivative over here is the sum from 0 to infinity of nx to the n minus 1, like this, if I do the power rule for my series here. So let's see here. So if now one thing that some people tell you is, okay, now we need to change this index up to n equals 1. And why are they telling you that? It's because if we plug in n equals 0 in here, we'll have x to a negative power. And that's something we shouldn't have for power series. But the reason why it's optional to do that is what's the coefficient for x to the negative 1? It's going to be n equals 0. So yeah, you would technically have a 1 over x right there, but it's just going to be zeroed out. And another more visual way of seeing this is if I were to write out the first few terms here. These are the first few terms of my series. 1 and equals 2 like that. And I were to differentiate each of these, what's the derivative of 1? It's going to be 0. What's the derivative of x? It's going to be 1. What's the derivative of this? Is going to be 2x. So you see, it's okay to have an n equals 0 term there because it's 0. So there's really no issue with keeping your index n equals 0. But some people like to just get rid of it and move it up to n equals 1. And that's totally fine too, because it's 0 here. Yeah, I guess I am a bit unorthodox in that a lot of people do like to shift the index. Reason being is that if you look at this function, some might say this is like not defined at 0 or something like that. But honestly, it's not a big deal really. On all of the exams, I'm gonna write it in this form, but you could do it in the other form too. There's no problem. All right. Anyways, I wanted to clarify that before I continued here. All right. Let's see here. All right. So now we want to find the area enclosed with r squared equals cosine of 2 theta. All right. So my biggest suggestion, the only suggestion I can kind of offer you guys in general besides practicing is draw the picture when it comes to these polar curves, because they're pretty strange. And this one is particularly strange, actually. So it's very important that we draw these. All right. Let's see here. Now, the interesting thing about this one is that our theta, or sorry, our r is actually squared right here. So that's a little bit different from normal. Usually we just have r equals something, but this is r squared. So what I'm going to do is I'm going to have a chart for theta, for r, and then for r squared right here. All right. So let's start drawing this. Let's start with theta equals 0. That's usually a safe place to start. So 0. Let's see here. So if I plug 0 in for this, I have cosine of 0 is 1. So that means my r squared is 1. But if r squared is 1, what can r be? My r squared is 1. What are the possibilities for r? That's right. So 1 works, obviously, but also we can't forget about -1. So this means that theta could be, when theta is 0, r could be plus or minus 1. Both of those points would be acceptable, and both are actually on the graph. So what I'm going to do is I'm going to have r as -1 at theta equals 0 here, and then I also have it right there as well. So I'm technically drawing 2 points at once if we think carefully about this. All right, next I'm going to go to maybe pi over 8. Reason being is that this has a 2 theta in it, so this will be more convenient. If I put pi over 8 in here, I have cosine of 2 times that, which is cosine of pi over 4. That means that r squared is root 2 over 2. And then that consequently means that r is plus or minus the square root of root 2 over 2, which is technically 1 over 2, or to the 1. So this number is going to be less than 1. Wait a minute. Well, all right, what's going to happen is it's going to kind of come out here a little bit. So we have this as being our r is 1 over 2 to the 1/4, which is the same as this number. But then we also have the negative version happening as well. So we're simultaneously drawing 2 different curves. This is the graph of r squared. It's the graph of r squared because r squared is what we want for this curve. So I'm technically drawing r squared. Both of these curves are r squared is cosine of 2 theta. Okay, now what's going to happen if I keep going to pi over 4? Cosine of 2 times pi over 4 is cosine of pi over 2, which is 0. And so we have 0 for this. Now, unlike the other ones, if r squared is 0, then that means r is just actually 0. So we're going to kind of wind our way back in here towards 0, like this. All right. Now notice that I drew, so if we focus on the positive part here, notice that I drew something that looks like this. It's kind of like half of a petal. And it turns out that if we go back through negative theta values as well, we'll end up drawing the mirror image of this as well. So this is what our curve is going to be here. I think I also talked about this in class as well. This is an even function, so it's symmetric vertically. So it's symmetric up and down. So since it looked like this up here and that down there, it's going to have to look like this up here and that down there. So effectively, what this curve is doing is it makes a figure 8. Now, what I could do to get the area within this curve is I can go from 0 to pi over 4 and get all of this. And then what would I multiply that by to get the area for the whole thing? 4, that's right. So that lets me set up my integral here. And this would be very hard to determine. There's actually probably no way I would have seen to do 4 times 1/2 the integral from 0 to pi over 4 of cosine of 2 theta if I didn't draw this picture. So like I said, drawing the picture is essential for this. And we could have kept going through here. We could have went to like pi over 2 and stuff like that to make sure it looks like this, but you could also use symmetry if you're comfortable with that. Why is it pi over 4? So r squared with theta equals 0 goes out here, and then this is like pi over 8, and then pi over 4 we come back into 0. So the way I'm shooting out my area here is like this. There we go. So shouldn't the cosine of 2 theta be squared? That's also another point about this problem, and the answer is no. It doesn't need to be squared. Because remember, the area formula for polar is 1/2 the integral of r squared d theta. But in this problem, our r was already squared, so we don't need to square it again. So actually, the integral for this one is particularly easy. But yeah, whenever you have r squared as something, don't square it again for your area. All right, this means that we're just doing 2 times the integral from 0 to pi over 4 of cosine of 2 theta. And then I'm going to integrate this. So I end up with sine of 2 theta from 0 to pi over 4. And notice that this 2 went away right here. So that 2 went away. Where did the 4 come from? It came from the fact that we have 4 pieces to this. So we have this one, this one, this one, and this one. So if I find the area within this piece right here, then I could just multiply everything. All right. Let's see here. So we have this, and then we plug in pi over 4 in for here, and we have sine of pi over 2, which is 1. Surprisingly, this whole figure 8 ended up having just an area of 1. So anyways, that's how we did that one. This was a very tricky one to draw here. So yeah, definitely important that we draw it so we know what our integral is going to have to be here. All right, wonderful. So we got this one done. Let's scroll all the way back up here, see what else we have. All right, so this was number 3 on assignment 20. Ivanica wants to do 6 and 5 on assignment 20. So let's take a look at that next. All right. Let's see. Between the two of these, I think I'm going to do number 6, and then maybe we'll come back to number 5 later. Okay, so homework 20, number 6. Let's take a look at that. All righty. So we want to find the area enclosed within r equals 1 and to the left of r equals theta squared. So this is kind of interesting. This usually we do like within or outside of, but this one just says to the left. We definitely need to draw a picture here to see what's going on. All right. So one of these we can draw without any effort whatsoever. What kind of shape is r equals 1? What is that going to be for polar coordinates? That's right, it's a circle. Yeah, Evan drew a big O here. That's right. So we have 1, and we have our circle. That looks like this. There we go. So that's r equals 1. That's centered at the origin here. All right, and then now we have r equals theta squared. So that one we're going to have to draw out. Well, let me make a table. Theta r. Let's start at theta equals 0. For this one, let's see, if theta is 0, well, then r definitely has to be 0 as well. So it looks like we're starting at the origin for this. Now let's maybe do like theta equals 1/2. Now, traditionally, we usually use unit circle values, like common angles for that, like pi over 4, pi over 3, and stuff like that. Oh, whoops, sorry, my camera got all messed up. There we go, sorry about that. Yeah, usually we use common unit circle values for this. But the thing is that common unit circle values aren't as great for plugging in to something like that. So we'll kind of have to guesstimate where these angles are. So if I plug 1/2 into here, that's going to give me 1/4 for theta. Now, 1 radian is about like 50-ish degrees. So 1/2 of a radian, that's probably like 30, kind of close to 30-ish degrees, maybe a little less. So we're going to kind of pop out only to 1/4. And then now what happens if I plug in maybe like theta equals 1? Then if I square that, I get 1, so my r will be 1. All right, so maybe right around here or so, we're going to go out to r. And this is actually where we touch the circle because our r is 1 and r is 1 for the circle as well. Then if we keep going, let's say we maybe go to theta is 3/2. This is around pi over 2. Then we're going to have 9/4 for our r, which is roughly 2. So this will expand all the way out here because this is bigger than 2. So what's happening is this spiral is shooting out very fast. And that's actually what it continues to do from there on. That's what our spiral looks like. Now, one thing you may notice is that, okay, so you said to the left of this, I guess that makes sense right here, but what does that mean for down here? How does that make sense? Well, in my hint here, I reminded you guys that theta could be negative as well. And while we usually don't care about negative theta values because we could just wrap around by going through like 2 pi or something like that for a lot of trig functions, if it's a non-trig or non-periodic function, we should consider what happens with negative values. So I'm going to make another table. I'm going to do the same thing, only with negative values. So let's say I go to theta as negative 1/2. Well, that means my r will still be positive 1/4 because I'm squaring, right? So I'm going to kind of come out here to positive 1/4. And then I have negative 1 here. And when I square that, I'm going to get 1. So I have that right there. And then when I go to say negative 3/2 here, then I'm going to have 9/4. I'll be out like this. So this spiral here, and this is going to spiral down this way as well. This is kind of like a double spiral. We have a spiral coming up like that, but then we also have one going down there. And now I think it's relatively clear what we mean by to the left of it, and also within the circle. Within the circle is here, but then to the left of this means I'm kind of missing this little chunk right here. I'm going to be focusing on that right here. Okay, now from drawing this picture, I see that we have some symmetry once again. Someone, I think in the chat, pointed out earlier that symmetry seems to be really common. Yes, it actually is with polar curves. Symmetry does end up being very common with the ones that we use. So we can exploit that. So what I'm going to do is I'm going to figure out the area in this chunk, and then I'm just going to multiply it by 2 to get the area for the whole thing. All right, so let's see. So how am I going to get the area for this curved part? Well, remember, the key thing to remember for doing these polar coordinates is we're effectively shooting out a laser from the origin out to the curve. And the curve we're touching here isn't the circle, it's r is theta squared. So my lines will shoot from the origin out to theta squared until we hit the intersection point, then they'll follow the circle. And remember, this intersection happens at theta equals 1. So I'm following r as theta squared up to here, and then I'm following the circle for the rest of this until I get to theta is pi. So my formula is going to look like this. My area will be 2 times the following. 1/2 the integral from 0 to 1 of theta squared squared, because remember, this isn't r squared this time. This is going to get me this little divot right here. And then I have my integral from 1/2 from 1 to pi right there. And the formula for this, r squared, will just be 1. I have 1 e theta. And thankfully, these are 2 very easy integrals to do. Okay, so the 2 will cancel with these 1/2. This is like a theta to the 4th. So if I use the power rule, I have theta to the 5th over 5. And then I have from 1 to pi here. If I plug these numbers in, I end up getting 1/5 plus pi minus 1. Is pi minus 4/5 right here. That's going to be my area here. All right, so we have some questions here. Why did we choose pi? Because pi is this angle right here. This is the angle pi. And I noticed that I have half of my area there, so then I just double it to get the rest of the area. So that's why I picked pi for my upper bound for this. Can you explain how you went from theta values to radians? I don't know. This is definitely a loose approximation, but I like to think of 1 radian as approximately pi over 3, like this. Oh, I'm really sorry. I need to go get my door here. Sorry, I'll be back in a second.
All right, so I have a question. I don't know if anyone can answer this, but since he's gone, I just want to ask real quick. So he has this little table thing on the left side of the paper where he's plugging in theta values and finding R. So and then he grabs it. So are you kind of guesstimating the distance with R, and the theta value kind of serves as like it's like the rad version of the like the
Yeah,
pi values?
yeah,
Okay.
that's right. I mean, I don't really know where 1 radian is on a 2 pi graph, so we just kind of guess. It's like it doesn't really matter what it looks like. All that matters is that we know that it crosses at 1.
Okay, but you can't. But like when he sets up this integral, you kind of almost guesstimate what the bounds are. Like,
No, with the bounds itself, you know for a fact, like we know that at theta equals 1 is where the 2 graphs are going to cross.
okay,
We just
that
don't
makes
know what that
sense.
looks like.
Yeah, I get it, because like the whole thing, the outer, like it goes all the way to 1 for the whole unit circle thing. So
Yeah.
it can never. Okay.
Yeah. And it's like we know that it crosses at that exact point. We just don't know any other point, or we don't know how to graph any other point except for that one.
Okay, but then for the R equals 1 value where it becomes pi on the bound, like how does he get that boundary from 1 to pi?
From 1 to pi, because he's just using the straight line to like cut the graph in half, basically because it's mirrored across the x-axis, so it's the same on the other side too. So you only need to go to that line, and that basically protects us from having to do the rest of the integral all the way down to 2 pi minus 1, which is what would be the bottom half of the graph. We could just solve the first half and then double it instead. It's you could keep going. That is a possible solution. It's just more difficult, and Manly didn't want to do it.
I got you. Wait, so the whole circle is 2 pi minus 1.
Well, where the bound crosses on the bottom part of the graph is at theta equals -1, right?
Oh, okay.
But if we're going there from a positive value standpoint, we're going until 2 pi minus 1, which is the same point. Oh, Manly's back.
Oh, all right, there you go.
You can ask him too.
Oh, I'm
He
really
might be
sorry,
confused
guys.
by it.
That took longer than I expected here.
Oh no, you're
Um,
good. We were having a discussion. I have a question for you. Actually, maybe you can help with this too. I'm
yeah.
some confusion. So when you drew this graph, and I get how you found the bounds for the first integral, but for the second integral, the 1 d theta. So I get that like the bound, like the circle itself crosses on the y-axis from like -1 to 1. But like how do you get pi for the upper bound of that integral? Because
Well, the key thing to remember is that we're not integrating with respect to like x or y or anything. We're integrating with respect to theta. So this means that my bounds are also going to be angles as well. So the circle, I'm going to start following the circle starting from the angle 1, like literally the angle 1, which is about 60-ish degrees. And then I keep going through the angle pi over 2, and then 3 pi over 4. And then finally I get to the angle pi, and then that's where I choose to stop following the circle, because then I could use symmetry. That's why my bounds here are 1 to pi.
all right, thank you.
Yeah, no problem. All right. Let's see here. But yeah, anyways, I like to use this as kind of a rule of thumb. 1 radian is often very close to pi. I think it's only a few degrees off. Yeah, Sophia, what's your question?
I had a quick question on on homework 16 on problem hold up, sorry.
Oh, Sophia, I don't mean to be rude, but I'm trying to go in the order that that I see these in the chat. So if you type it in the chat, I'll eventually get to it.
Oh, okay, yeah.
All right, let's see here. Scroll back up here. You talk about, Daniel wants to talk about non-zero terms in the nth degree Taylor polynomial. Yeah, so let me explain what I mean by that, because I think some people have gotten confused about that before. So let's say I want you to find the second degree Maclaurin polynomial of something. That means I want you to find some number plus some number times x, and then some number times x squared, and then you could stop there. And one way of doing that is by making your Taylor series table, but then just stopping at n equals 2, because that would be right here. And remember, this has the formula nth derivative at 0 divided by n factorial. Now, whenever I say the first two non-zero terms, that means I go through this list here, so A0, A1, A2, until I have two terms that are written down that don't just go to 0. And let's say, for example, in this instance, the A0 is 1, A1 is 1, and A2 is 1. So if I wanted to list the first two non-zero terms, that would be 1 plus x. That would be what that would be here. But on the other hand, if I maybe had like A0 is 0, A1 is 1, A2 is 1, then I would ignore the first one. That wouldn't count at all because it's 0. And then I would do A1 is 1 and have my x. And then I would do A2 is 1 and have my x squared. This is what I mean by first two non-zero terms. We keep writing out terms in this infinitely long polynomial or power series until we get however many there are written down, and 0 as a coefficient doesn't count. That's the difference between these. Whenever it says a certain degree, we go up to x's whatever that power is, no matter how many terms it takes. But for this one, for the first two non-zero terms, that means we just keep writing out terms from the power series until we have however many of them that aren't 0. And one more point of clarification, non-zero does not refer to the index. So even though this index is 0, we still count the 1 right there. It's talking about the value of this being 0. So that's how we handled that bit right here. How's that chat missing it?
Well, Professor Manwing, just a quick question on this.
Mhm.
So for the first one, like the second degree Maclaurin polynomial, the degree of your approximation is 2, right?
Mhm.
And then for the first two non-zero terms, the first example where it's 1 plus x, the degree of your approximation is 1 there.
That's right. Yeah, your degree of your approximation is whatever the highest power of x
Power
is.
is. Okay.
Yeah, so that's how that works.
Okay, perfect. Thank you.
No problem. All right, good. We got that. That was a good question. Let's see here. Can we do 17 on exam 3? Yeah, absolutely. Let me get that up here. All right. Practice exam number 17. Find the area enclosed within both r equals 1 and r is 1 minus cosine. All right. Who is this Maclaurin guy? I actually know pretty much nothing about Maclaurin as a mathematician. I just know he has these series named after him, so your guess is as good as mine. All right, so practice exam 3, number 17. Let's see, so we have r equals 1 and r is 1 minus cosine theta. And we want the area to be enclosed within both of them. Okay. So as always, let's draw the picture here. This will definitely help us get an idea of what our bounds for our integral should be. All right, so let's see, r equals 1. We drew that for the last problem, actually. Just a circle of radius 1, like that. All right, so we got that one. That one's pretty easy. Now for this one, we're going to have to plot some points to see what's going to happen with this. Some of you may actually recognize what curve this is, and if you do, that's wonderful, but let's go through this just in case we don't. If I put in theta equals 0, I have cosine of 0, which is 1, and then 1 minus 1 will be 0 right there. All right. I'm going to go to pi over 2 next. I don't think there's too much interesting stuff that happens between here. If I put pi over 2 into here, cosine of pi over 2 is going to be 0. So my r value will be 1. So I start from 0, and then I expand outwards until I hit 1 right there, which coincidentally is also where the circle is. Then if I spin all the way to pi, I have 1 minus cosine of pi, and cosine of pi is a -1, so I'm going to get 2 here. So spin outwards like that. So this is 1, and then that's 2, out like that. And then finally, so I could keep plotting points and drawing this, but remember, this is going to be an even function, so we could use symmetry to draw this. But let's keep plotting points, just in case we didn't see that. We have 3 pi over 2. Cosine of 3 pi over 2 is 0, so I get 1. Come back in here. And I'm hitting 1 as I get to the angle 3 pi over 2. And then finally 2 pi. And this is 2 pi periodic here, so this should be enough. I end up getting cosine of 2 pi is 1, so 1 minus 1 will be 0. All right, so then we end up getting this, this cardioid. Sydney's asking a very good question here. Why do we make a curve and not do a line? Because remember, polar coordinates, by default, they're better at representing circles. So if you wanted to kind of draw like a generic curve with polar coordinates, you make it circular. That's why all of our curves end up being so puffy, because we're effectively drawing little circle arcs as we go along. So that's probably a better way of thinking it, connected almost with circles rather than lines with polar coordinates. All right, now we want it to be enclosed within both of these. So this is right here, and then the circle's here. So the intersection of them, meaning like kind of almost like the Venn diagram for these, would be kind of like this. But actually, it looks remarkably similar to the problem that we did earlier, only this curve is a bit different from before. All right, so I'm going to do this in exactly the same way that I did my other problem earlier. I'm going to follow this curve from 0 to pi over 2. I guess that's different. We're not going to 1 this time. Do 0 to pi over 2, I'm following the cardioid, 1 minus cosine of theta. And then once I get to pi over 2, I'm not following the cardioid anymore, I'm following the circle. So I go through like that. All right, and then I'm going to double this because I think it's pretty clear this is symmetric here. So my area will be 2, and then we have 1/2 the integral from 0 to pi over 2 of 1 minus cosine of theta squared. So remember, we can't forget to square this when we do our area formula. And we can't forget the 1/2s either. It's so easy to forget that 1/2, especially when it goes away with symmetry. All right, and then let's see here. So once we start following the circle here, we go from pi over 2, and we keep following that until pi. Pi over 2 to pi, and we would square this formula, but squaring 1 is just going to give us 1 right here. And then we just double our result because this area will be exactly the same as this area down there. So we really only need to do one of them. All right, and there we go. And I think in the interest of time, I think I'll save the integral for you guys to do. This would happen, so the 2's and the 1/2 would cancel out. This one we would FOIL and then use a half angle identity to finish that off. And this is just going to be theta. That'd be how we would do the integral there. But I want to make sure we have time to get to everyone's questions. All right. Let's see here. Let's go back up. That was a good problem. All right. Let's see. Peter would like to go over number 7 on exam 3. All right, let's take a look at that. Okay, so this one's going to give us practice using the Taylor remainder estimate, which is the more difficult of the two estimates to use. Usually we want to use the alternating series one when we can. All right, so practice exam 3, number 7. So it depends on the previous problem here, so I guess we have to look at that. So the previous problem wanted us to do the integral from 0 to 1/2 of e to the x squared dx. Okay, so I think we first need to kind of see what happens with this, and then we'll have enough information to finish this off here. All right, so let's see. So we need to get a series for e to the x squared. So e to the x is the sum from 0 to infinity, x to the n over n factorial. So that means that e to the x squared will be the same thing, only with x squared to the n, or x to the 2n. All right, so this is our series here, and then we put it into an integral. So we have 0 to 1/2, the sum from 0 to infinity, x to the 2n over n factorial. And as always, the beautiful thing about series is that you can integrate them just like polynomials, and there's no problem with that. So this is going to be the sum from 0 to infinity, x to the 2n plus 1. Then we have 2n plus 1 times n factorial down there. This is from 0 to 1/2. And then finally, we plug in 1/2 right here. So we have 1/2 to the 2n plus 1 divided by 2n plus 1 to the n factorial. If I'm not mistaken, I think they wanted us to use the first two non-zero terms of the series for this. So this is good practice for what that means. I'm going to plug in n equals 0 into here. So let's see, I have 1/2 times 1 times 1, so that'll be 1/2. And then I also, if I plug in 1 here, let's see, I'm going to have 1/2 cubed, which will be an 8, times 3, which will be 24, times 1. So I end up, so we actually ended up just doing problem 7 here. This is going to be our approximation here, 1/2 plus 124. All right. Now, for the next problem, we want to figure out the maximum amount of error for this. So notice that if we go back here to our x's, right, we used n equals 1. That was the last thing that we used here, n equals 1. So that means we technically, this came from an x, and then this came from an x cubed. So that means that the degree of this approximation that we used was a degree 3. So that means that the n we're going to use for our formula is 3. Oh yeah, and let me remind you guys, the error formula for this is always going to be less than or equal to m times the absolute value of x minus a to the n plus 1 divided by n plus 1 factorial, like that. All right. So now we just need to fill in x, a, n, and m. And for this one, I actually told you what two of these things were. I said that m was 24 and n is equal to 3 right here. Well, why is this a third degree approximation? Because technically, when I plugged in my 1/2 for my n equals 0 and n equals 1 term, well, notice that up here, if I put in n equals 1, I have an x cubed up here. So since the biggest power of x that I used for this was x cubed, then that means it's a third degree approximation. All right. How would we get m equals 24? There's a lot of behind the scenes for that one on this problem. Getting m for that's rather difficult. So we're gonna skip that for now. But anyway, so we know what m is. It's 24. Now we need to also put in what x and a is. So x, what was the x value that we used earlier? It was 1/2. And what's the a value? Well, a is the center of our series. So a is going to be 0. So I have 1/2 minus 0 raised to the 4th power divided by 4 factorial. All right, now coincidentally, 4 factorial is actually the same thing as 24. So these will cancel out. And then I have 1/2 to the 4th power is 1/16. So what is this saying? It's saying that this approximation here, 1/2 plus 124, it's no more than 1/16 away from the true value of this integral right here. That's what this error is telling us.
Are you gonna? Oh, sorry.
Well, so people want me to explain why n is equal to 3. So if I go back to this series here, this is x, I plug in n equals 0, and then it's going to be x cubed over 3, and then so on. So the way I got my number here is I plugged in x is 1/2 in for this, because that's what I needed to do for the integral. And my highest power of x that I used was 3, so it's a degree 3 approximation. Was m equals 24 given? Yes, it was. It's difficult to figure out what the m is for this one. You need to take like a few derivatives of this and then do some weird inequality stuff. So if it's not something really simple to get the m, I'll give it to you. And this one, it's really hard to get the m, so I gave it to you. So I wouldn't worry too much about that. The only time I might not give you the n is like, let's say your f of x is like sine of x, and maybe we're approximating like, I don't know, like sine of 0.1 or something. Then any derivative of sine or cosine will be a sine or cosine. So if we look at the nth derivative with some c value plugged in, well, that's got to be less than or equal to 1 no matter what. That's going to be our m. So if you ever have sine or a cosine, and that's what you're using for your inequality here, you immediately know you can use m equals 1 for that. How do we know to do only the first two terms? Because the problem asks you. Let's see. So the n in the Taylor series approximation is always the degree of the polynomial. Well, we got to be careful here. So n equals 1 gave us an x cubed term. So this n may not match the power of x, but the degree of the approximation is talking about literally the degree of the polynomial. So since it's degree 3, that means our biggest power of x is x. Douglas, do you have a question?
Yeah, just a quick question. About the degree approximation, you'll always give us that, like the n, right, for this type of question? No.
Not necessarily. I think I gave it to you for this one because there's an integral involved as well. So I thought people might be confused because we started with an x squared back here. But I might not always give it to you.
So if you didn't give it, then how would we go about?
You just look at the series that you're using and see what the highest power of x that you used for it is. So I asked you to use the first two non-zero terms, right? So the first two non-zero terms of the series are x and x cubed over 3. And since the biggest powered one is cubed, it's a degree 3 approximation.
Okay, thank you.
All right. Let's see here. That was a good one. Let's go back here. Can we do number 1 on the practice exam? I think we did that one. We go over 9 on practice exam 3.
I have a question about n.
Yeah, what's up?
So on the notes, it says that the big N should be the partial sums. So like, wouldn't that be 2 in this case and not 3? Because that's the degree.
Technically, the partial sum for this one would actually be S1 because we're adding A0 and A1 together here. So this, if we wanted to write out that partial sum notation, this would be what we would do. But the n in this formula, this isn't the n for the partial sum. This is the n for the degree of the approximation. So this n and
so
this n might be different.
So the nth degree Taylor polynomial.
Yeah, the nth degree Taylor polynomial, that'll be this n.
Okay,
right
so
here.
that's basically the degree of the series?
That's right, yeah.
Okay, so not the partial sum, the degree of the series.
That's right.
Okay, I'm just making sure, thank you.
All right, so let's do number 9 here. This is another opportunity to use series right here. Some practice with that. All right. Okay, so this one wants us to use the 3rd degree Maclaurin polynomial or tangent of x to approximate tangent of 1. All right, so tangent of 1 is certainly not a common tangent value on the unit circle, so we're going to use our 3rd degree Maclaurin polynomial to help us find it. All right, now tangent of x isn't one of the common Maclaurin series, so we might need to make this one from scratch. I'm just going to make the table for this guy. All right, we have our nth derivative at x, we have our nth derivative at 0, and then we have our nth derivative at 0 divided by n factorial. And since it's a 3rd degree Maclaurin polynomial, I need to go until I get the coefficient for x cubed here.
Oh, Professor Manley?
Table off to 3. Yeah, what's up?
Oh, sorry to interrupt, but when I did this question, I thought it was a lot easier if you just take the first couple terms of sine and the first couple terms of cosine and end up dividing them. Like you do sine over cosine.
Yeah, you need to be careful with how you do that, but yeah, you could use long division.
Yeah, that's how I did it with long division.
If you want to. Yeah, that's totally fine to do that as well. I'm going to do it this way, though. I don't think it'll take too long. But yeah, you can use long division if you want.
All right.
All right, so the 0th derivative of my function tangent is, well, tangent. Then I have tangent of 0 is 0. So I end up with 0 for my first coefficient. All right, I do the derivative of tangent, I get secant squared. Secant squared of 0 is now 1, and 1 over 1 factorial is going to be 1. All right, now I need to do the derivative of this. It gets a little trickier. If I use the chain rule, I take the derivative of something squared, so I have 2 times that thing, but then the derivative of secant is secant times tangent. So I multiply this by secant times tangent, but I already have a secant, so it'll become secant squared. Then I have my tangent right there. Now, if I plug 0 in for this, the secant's not going to matter at all here. It's mostly tangent of 0 is going to dominate because the whole thing wanted to be 0. All right, and then finally, I need to take my derivative of this. Let's see here. So if I use the product rule for that, I have 4 secant squared of x, tangent squared of x plus 2 secant to the 4th of x like that. And when I plug in my 0 for this, it's going to give me 2 right here. And I do 2 over 2 factorial, that'll just be 1. So it turns out that tangent of x is approximately equal to x plus x cubed. So this is going to be our 3rd degree Maclaurin polynomial. And notice that we're skipping these two, a0 and a2, because they're 0, so we don't care about those. All right, and then now we want to approximate tangent of 3 factorial. No, you're right. I thought something looked a little funny. Sorry, this should be 1/3 instead. There we go. Thank you. Thank you for the correction there. Yeah, this should have been 3 factorial, not 2 factorial. All right, so we get 1/3 for that. Anyways, I'm going to plug in tangent. I'm going to plug in 1 here. We're going to have this is approximately equal to 1 plus 1/3 here, which is going to be 4/3. 4/3 is going to be our approximation for tangent of 1. That's how this one is going to go here. All right.
Oh, Professor Manley, do you think you could show us how to get M for this problem? Like if we had to do the Taylor remainder estimate?
M for this would be really gruesome. I would definitely not ask you to do that. I actually was thinking about putting that on the practice exam, but then I did it myself, and the M turned out to be like 1,080. So this is not a good problem to try that with.
Okay. So if we had like M, it would be something where you give us like sine or cosine or something along those lines, where it's like easy to get.
If I want you to find it yourself, then it'll be something like this, or maybe at worst, I'll be like, okay, approximate E being less than 3 or something like that.
Okay.
That's what would be as hard as it is. Like even this one back here when M was 24 was too much, so I just gave that to you. So yeah, I wouldn't worry about that.
All right, thank you.
All right.
Professor Manley?
Yeah, what's up?
Where did the x plus x to the 3rd over 3 come from?
So our whole goal was to find a 3rd degree Maclaurin polynomial. So since I got my a1 being 1, that goes next to x to the 1st power, so it's 1 times x to the 1st power. And then I have 1/3 times x to the 3rd power. That's how I got this. So the numbers that we find in the last column of this table, they're the coefficients for the matching x to a power for there.
Thank you.
Yeah, no problem.
For when you make a table like this, are you plug in the center?
Yes, you always plug in the center of the series. So if I center this at 1, for example, I plug 1 in for all those.
Okay, thank you.
And Jenna asks, if it asks us to find a certain degree, we only have to put in as many n as we need to get to the degree. Yes, you do. So you don't need to find the general Maclaurin series for tangent, which is actually a little bit complicated. You only need to get up to n equals 3. So yeah, you can stop there. You don't need to find a general pattern. All right, wonderful. That was definitely a good practice one. Let's see here. Back up here. Let's see. Do number 3 on the practice exam. Let's see here. Yeah, this is a good one to try. Yeah, let's do number 3 on the practice exam. Okay, so for this one, we have this function, x over 1 minus x quantity squared. And we want to find the power series representation for this function. All right. So what we need to do is we should probably start with a familiar looking power series to begin with. And the closest one to this is the one for 1 over 1 minus x, which is the sum from 0 to infinity of x to the n. All right, now I noticed that my bottom is squared here. And I know that if I take the derivative of both sides of this, in the process of doing so, I'm also going to square the bottom of this. Because if I do the derivative of this function and its series, then I end up with 1 over 1 minus x squared. As I do the power rule on this, this is to the -1. So I technically have a negative there. But if I multiply by the derivative of 1 minus x, which is -1 as well, that will go away. Then I have my sum from 0 to infinity, or 1 if you like, as we discussed earlier. And we have nx to the n minus 1 right here. Now, all we need to do to get this series to match the one we have is just multiply by x. So if we multiply both sides by x, then we end up having our series here. And as always, we like to write our series in the form where we have all the x's combined together. This is sum from 0 to infinity, n x to the n, right there. And there we go. There's going to be our series for this function right here. This is actually relatively simple looking.
Dr. Manley?
Yeah.
So you can take out the x when you derive it and then just put it back in at the very end? Like,
it's more like I didn't introduce the x until the end of the problem. So like I constructed this function, then I just stuck an x in there.
Okay, gotcha. Thank you.
Let's see. Savannah asks, we always try to make the given function match the basic function or vice versa. That is a very good strategy, especially if you want Maclaurin series, because that's what I'm going to be providing you on your little cheat sheet thing. So yes, yeah, that is often a good strategy. Won't work all the time. Like for example, back here, it's a little bit tricky with tangent because nothing looks exactly like tangent on the sheet. But yeah, most of the time, if we can do that, then we should. Is it supposed to be a negative on the derivative? Oh, okay, yeah, you saw that. All right.
Dr. Manley?
Yeah, what's up?
I just wanted to clarify. Is it better to always match the given to the basic 1 over 1 minus x function or vice versa? Because I saw you did more of the work.
I would start with the basic one and try to get it to look like the one that you were given.
Okay.
Yeah, I would like keep modifying it until it gets to where you want. That's usually.
And like, just for clarification, I was a little confused on that. Would you always start with finding the derivative, or start with the integral, or just whichever you need in the moment?
It really depends on the situation. If I see the entire bottom raised to a power, I know that happens to differentiation because of the power rule. So that's why I chose to do that here. But if like say the square were only on this x right there, then I might substitute x squared into the geometric series. So unfortunately that one, it just depends on the situation.
Okay, thank you.
No problem. All right, let's go back here. Still don't think I've gotten all of them at the top here. Matthew would like to go over number 5 on the practice. Let's see. Okay, so this one talks about the other way that we find error, the easier way, using the alternating series remaining estimate. And this one's more accurate and easier to do when you have an alternating series, but unfortunately life isn't kind enough to always do this. But in this case it was. So we have to do question 4 first, before we can even do question 5. Or alrighty.
Dr. Manley, I have a quick question for you from the previous one. When you're doing the derivative of 1 over 1 minus x, where is the negative?
So I did the power rule on the bottom, right? Like this is 1 minus x to the negative first power.
Yes.
And so if I do the power rule, I have negative 1 minus x to the negative second power. But by the
Yes.
chain rule, I need to multiply by the derivative of the inside, which is also -1. So those negatives ended up canceling out.
Okay. Okay. Thank you.
All right, so this problem, so this is the other end of the spectrum here when you guys asked between the difference between degree and first few terms. This one wants us to use the first two non-zero terms of arctan of x to approximate arctan of 1/2. I guess I should clarify the first two non-zero terms of the Maclaurin series. All right. So let's see here. Let's go ahead and get started here. So the series for arctangent is one I'm going to be providing to you on your sheet here. And that is -1 to the n, x to the 2n plus 1 divided by 2n plus 1. Like that. All right, now we want to use the first two terms of this series, right? So let's plug in 0, see if that gives us a non-zero term. Let's see, I have -1 to the 0, which is 1. I have x to the 1, so that's an x. And then I have 0 plus 1 is 1. My first term is x, and x is non-zero. All right, and then I go to n equals 1. I have a negative here. I'm going to get x cubed, and then it looks like I'm going to have a 3 down there. All right, so I successfully have two terms, and neither of them were 0, so I could stop. I found the first two non-zero terms. And notice that the degree doesn't matter. The degree actually didn't equal 2. The degree was 3. So the degree has nothing inherent to do with the first number of terms. All right, so this is my approximation for arctan of x. So that means that if I want to approximate arctan of 1/2, that's going to be about 1/2 minus 1/2 cubed over 3, which is 1/2 minus 1/24. I think the answer to the other one was 1/2 plus 1/24. But this one's 1/2 minus 1/24 instead. All right, but that was the answer to number 4, but you didn't ask me about that. You asked me about 5. 5, we want to use the alternating series remainder estimate to get our maximum possible error here. And this is an alternating series, so we can do that. Now, the next term we would have added into this series if I were to continue here would have come from n equals 2. So that would make this positive. Well, actually, we don't care about that. We ignore the alternator. We have x to the 2 times 2 plus 1 would be x to the 5th. And then we divide by 5. But in our problem, remember, we used x as 1/2. So the next term after the 2 that we used would be 1/2 to the 5th over 5. That's going to be greater than our error here. Remember, all we need to do for the alternating series remainder estimate is just go to the next term that we would have used after we stopped and just plug in the number into that. We have 1/2 to the 5th, which is 1 over 32, if I'm mistaken, times 5. So we get that our error for this is actually pretty small. It's less than 1 over 160. So this is how close, at worst, our approximation is to the true value of arctan of 1/2 right here. I hope this is the type of error for our exam. Well, I'm probably just going to give you both types of questions. So you'll have one like this and one like the Taylor one. So that's probably how it'll go.
When do you use the n+1 thing for error?
So that's if rather than doing the first two non-zero terms, we want to approximate it to a certain level of accuracy. Then we do the problem backwards. We do this error part first to figure out how many terms we need to add up. And then once we figure that out, then we add the terms together. So it's effectively, it's kind of like a backwards process if they wanted to be within like 0.01 level of accuracy.
Okay, thank you.
For finding the error, why did you get x to the 5th? Is that just n equals 2 is what you plugged in?
Yeah, so I stopped my approximation at n equals 1, and the alternating series approximation says that whatever your next term would have been, that's an upper bound for your error. So this was n equals 2, which is the next term after I stopped.
Okay, thank you.
All right, how many questions on this exam? That's a difficult question to answer because some of them are like kind of like multi-part. So I think there's technically 13, but some of them have multiple parts. Like I think I smashed together things like question 4 or 5. It'll be similar in length to this exam. I guess I'll say that. All right.
Is the exam gonna like mirror the practice exam in difficulty?
Oh, in difficulty, yeah, probably. Yeah, I would say so. It won't be
Okay.
like exactly the same questions. Like I won't just like switch number around or anything. But yeah, the difficulty should be around the same. At least that's what I intended. All right. Let's see.
So for this type of error, you don't need to find an M. Just making sure. Like it's just the next.
Yeah, no,
value.
the M only comes in when we do the Taylor remainder estimate, which we do for non-alternating. Then we have to figure out what M is or use it if it's provided.
Got you. Thank you.
I think I got lost where I was looking at my questions here. Did we do 8 on the practice exam yet? Is that a thing that we've done? No, we didn't do that. Okay. Oh yeah, that is the next question. Okay, good. I'm still looking at questions asked at 11:52 a.m. So I apologize. Let's see here. Let's do 8. Okay. Find the Taylor series for e to the x centered at a equals ln of 2. Okay. Now it may be tempting to kind of just throw in x minus ln of 2 on the Maclaurin series table and just call it a day. But unfortunately, it's a little bit more complicated than that. If you center your series somewhere else other than 0, chances are you need to make it use a table from scratch again here. All right. So let's see here. Let's do the table. I think this one will be pretty easy to come up with the pattern, though. I don't think we're going to need to do it for very long. All right, and then we have the nth derivative at ln of 2 divided by n factorial. All right, I think we'll actually see the pattern after only going to n equals 2, so let's only go that far. Okay, so 0 derivatives of this function, well, it's e to the x. Actually, we could fill in this whole column immediately. Any derivative of e to the x will be e to the x. So there's no issue with that. All right, now what I'm going to do is I'm going to plug a natural log of 2 in for all of these. And what's e to the ln of 2? Well, that's just going to be 2 because e and natural log are inverse functions. So we end up with 2 for all of those. And then finally, the last thing we have here is we divide by the relevant factorial. 2 over 0 factorial, 2 over 1 factorial, 2 over 2 factorial, etc. like that. So naturally, I think that we could see our an pretty clearly. It's just going to be 2 divided by n factorial. That's going to be our a sub n here. Now remember, this goes next to our coefficient of x. So this will be the sum from 0 to infinity of 2 over n factorial. And now we need to be careful. Since we center this at ln of 2, it's not just x to the n, it's x minus ln of 2 to the n. I know we usually work with Maclaurin series, so it's easy to just put x to the n in there, but don't forget to do x minus something if it's centered somewhere else. So anyways, this is going to be our Maclaurin, or sorry, not Maclaurin. This is going to be our Taylor series for e to the x centered at L. All right, that's a good one.
Professor Manley, sorry to ask so much about the M stuff. This is what really confuses me. So M in this case, would it be 2 because the derivative at the center is always going to be 2?
I guess for this one,
because like, let's say you approximated
about capital M, like if I wanted to do an error estimate on this.
Exactly, yeah.
So for this one, yeah. So our nth plus first derivative at c would always just be e to the c like that.
Okay.
And remember, c is some number between a and x, like this.
Mm-hmm.
So it depends on what x value you use. That's going to affect what m is.
Oh, okay.
But by default, this is going to be at least 2. because you're going to have
Okay.
e to the ln of 2. So your m's got to be at least 2 or maybe even bigger, depending
Oh,
on.
okay. Depending on the x, I see that now.
Yeah, you just need your m to be bigger than the c depends on x. So you have
Okay.
to give me an x value before I can do that.
All right, perfect. I understand it now. Thank you.
All right. Let's see here. Let's see. Can we go over why E is not in the final power series? So the whole point of these power series is to approximate things like e to the x. Where e to the x shows up is that we want our function to equal this series right here. So the e to the x, it technically shows up in this equation, but it shows up on the other side. It's not in the series. And these power series, they're always going to be something like x minus a to the n. Because the whole goal of these power series is to act like polynomials. Because e to the x, it's not a polynomial. But what we can do is we can add together a bunch of these terms, have an infinitely long polynomial, and get something that does look like e to the x. So we shouldn't have e to the x in here because we want this to equal e to the x. All right. So let me scroll back up here. Okay, I think, let's see, Nathalie asked about number 2 on this exam. All right, so let's take a look at that one. Okay, so practice exam 3, number 2. For this one, our function in question is going to be cosine of x times sine of x. And we want to come up with a Maclaurin series for this. Now, in theory, we could take the Maclaurin series for cosine and multiply it by the one for sine. But remember, just like polynomials, you can't multiply matching terms together with power series. You need to FOIL them out. And doing infinitely long foiling is not so great. So rather, for this problem, we're going to use this hint. Sine of 2x is 2 sine of x cosine of x. So if we want to get this, all we need to divide by is 2 here. And we see that sine of 2x divided by 2 is sine of x times cosine of x, which is what we want. So rather than finding the series for this, I'm instead going to find the series for sine of 2x over 2. That's a much more, much easier way to go. All right, so this is definitely using the Maclaurin series for sine. So sine of x, if we remember, or look at our sheet, is the sum from 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. So consequently, if we want sine of 2x, then we will substitute that in. So sine of 2x here is going to be the sum from 0 to infinity, negative 1 to the n. And then I put a 2 in here. So this will be 2 to the 2n plus 1, x to the 2n plus 1, and then 2n plus 1 factorial. All right, so there's my sine of 2x. Now, remember, I don't want sine of 2x exactly. I want sine of 2x divided by 2. So I'm going to divide both sides of this by 2, or multiply by a half here. All right, now notice I have 2 to a power already in my series, right? So I have 2 to the 2n plus 1 up here, but then I'm dividing by a 2 right here. That means that this plus 1 power will cancel out with that 1/2. Now I have 2 to the 2n, but that's the same as 2 squared to the n. So in summary, my series will be the sum from 0 to infinity, negative 1 to the n, 4 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. So there we go. So there is our series for this, which was also what we wanted originally. Cosine times sine. All right, so that's how we handle that guy. So if there ever is a hint, so if I say like hint, do this, you should really try to do that. I mean, I don't know, that might sound obvious, but yeah, if there's ever a hint for something, I'm giving that to you because I don't think that's like an obvious step or maybe something that's common knowledge, but it will be extremely helpful. So if I do give a hint, then I recommend that you take a look at it. And yes, there will be some hints for things that are kind of difficult to see on your own. All right, great. So we did that one. I feel like we've done like half this test at least. Let's see. Go over 3 and 9 on assignment 18. Carol, are you still here? Which one would you like me to?
Let's do number 3.
Number 3? Okay, sounds good. Let's see here. Assignment 18. I don't have that one pulled up right away. Let's see. This is back in the parametric days. Let's see. Number 3. Okay, suppose a particle moves along this path. So here's homework 18, number 3. All right, so suppose we have a particle and it's going along the path x squared plus y squared is 25. So if the particle's velocity in the x direction is 8 at the point 4, 3, then what's its y velocity? How fast is it going vertically? Now remember, with these parametric equations, there's a very strong relationship between them and physics. So if we want to write this in terms of parametric equations, velocity in the x direction, that's another way of saying dx dt. So we know in this problem that dx dt is going to equal 8, and it's going to equal 8 when x is 4 and y is 3. Now our problem here is to get the y velocity, so what we want to figure out is dy dt. Now this is another one where I give you guys a hint. So my hint for this one is you can solve this problem using techniques from Calculus 1. And then I also tell you to enter it as a fraction. So what Calculus 1 technique can we use here? Well, if we ever want to, we need to know what derivatives are, right? So we probably need to do some kind of derivative. But the thing is that t doesn't show up directly in this equation. And we could still take the derivative with respect to t, but we have to do it in a way which was called implicit differentiation. The way that works is we take the derivatives as if these were the independent variable normally, but then we slap a d whatever dt there because of the chain rule. So for example, for x squared here, the derivative of that would normally be 2x, but then I put a dx dt in there because x could depend on t. The same thing happens for y. And then if I take the derivative of 25, I don't care what variable it's with respect to, the derivative of a constant will be 0. So I effectively just did d dt of everything. All right, now my whole goal is to get what dy dt is. So first I'm going to divide by 2's, because 0 divided by 2 will be 0 still. And then I'm going to subtract this over here. So I have x dx dt is negative y dy dt. And then I'm going to divide by negative y. So I have negative x over y dx dt is dy dt. And then now I actually have all of the ingredients necessary to plug in over here so I can get dy dt. So x was x was 4, y was 3, and then this was 8. So we end up getting negative 32 over 3 for our dy dt. All right, so that's a little bit of a throwback there using some Calc 1. Let's see here. We get a problem of exam level with difficulty for each topic. Well, there are a lot of topics. That's kind of the point of the practice exam. I do try to make the practice exam similar in difficulty to the real one. So if you want something like that, I definitely recommend taking a look at our practice exam here. Can we do number 17 on the practice exam? I think we've done that earlier. So hopefully you got that answered. Can we do problems 3 and 8 on the April 2019? Yeah, absolutely.
Professor Manley, like as you're doing that, can you go over why you didn't like do the whole, I guess, like, because you have the equation of a circle that's Cartesian, and why you didn't, I guess, Actually, never mind. I was gonna say you could have solved for r because they gave you 25.
Oh,
But
yeah, if we wanted to put
I'm
this
not
in polar coordinates, you're right. You would have r squared equals 25, so r would be 5. But yeah, we were working with parametric equations for this one, so that unfortunately would have been too helpful. All right. Let's see here. So, let's see. I don't know if Sophia is still here. Would you rather do 3 or 8 on
Can you
April
do
2019?
number 3, please?
Number 3, absolutely. Let's see here. This is a good one. So this is spring 2019, number 3. All right. All right, so this time my function is x cubed e to the 3 minus x cubed, and that's all in the exponent here. All right. So what do we need to do for this problem? What they ask us to do is we need to
I think that's on
find.
the wrong exam. I think
Oh, is
number.
this? Oh, this is 2016. I'm sorry.
That's okay.
Let me pull up 2019. Let's see. Number 3 on that. Okay, well, this is another good problem too. So, all right, let's take a look at that. Sorry, spring of 2019, number 3 is this. We have this series 3 minus pi squared over 2 factorial times 3 plus pi to the 4th over 4 factorial times 3 cubed minus pi to the 6th over 6 factorial times 3 to the 5th, and then pi to the 8th over 8 factorial times 3 to the 7th. And presumably this pattern continues on. This should be enough information to find a pattern. Now, what we want to do is we want to find the sum of the series. But the problem with this is that it's neither, it's not, wow, I'm blanking here. It's not geometric or telescoping, so we can't use either of those methods to find the sum of the series. So instead, we need to do something else. Oh, can I straighten the paper? Yeah, sorry, I got a little messed up when I moved my camera. Okay. All right, so we need to find a way to sum the series. Now, what I'm going to do here is I'm going to try to find a Maclaurin series that looks a lot like this. Let's try to take a look at some of these patterns for hints here. Let's see, the first thing I see is that it's positive, negative, positive, negative, positive. So it should be some kind of alternating series. Let's see, I have a bunch of even powers of a number, and I have a bunch of even factorials as well. That's an especially big clue. So what series is alternating, has even powers of a number, and then even factorials? That's right. It's going to be cosine of x. So cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, x to the 6 over 6, x to the 8 over 8, like that, and so on. So remember, the radius of the interval of convergence for cosine is all real numbers. So I can plug in any x value I need to get this. Now, in particular here, I see a lot of 3's raised to a power and a lot of pi's raised to a power. That gives me the hint to maybe plug in pi over 3. We have cosine of pi over 3. That's going to be 1 minus pi squared over 2 factorial times 3 squared. Pi to the 4th over 4 factorial times 3 to the 4th, pi to the 6 over 6 factorial times 3 to the 6th, and then we have pi to the 8th over 8 factorial, 3 to the 8th. All right, now this is almost what we want. This is almost this series right here, but what do we need to modify to get these to be exactly the same as this? That's right, Miguel's got it here. We're going to multiply by 3. So if I multiply both sides by 3, then this will become a 3. This power will cancel out with 3, so it'll become pi squared over 2 factorial times a single 3. And the same will happen with all the other powers of 3. Those will all decrease by 1 on the bottom, which is exactly what we want them to do. So there we go. We end up having our series. So what does the series sum to? It sums to 3 cosine of pi over 3, which is 3 halves. This is an extremely complicated way of writing 3 halves if you want to. This is actually sort of a third method for summing series. You could also find the Maclaurin series that it's similar to, and then see what number that is if you plug in an appropriate x. So this is actually a third method for summing up series. This is how you get the sum of a lot of it. All right, great. That was a good problem. That's something we can do with series here. All righty. Going back up here, back in time to 1158. Let's see. Let's see. The next question at 1203 was Jenna. Can we do homework or number 3 from homework 15? Yeah, sure. Let me get my assignment out here. Assignments. Assignment 15. Okay, so this one wants us to find a series representation. Get some practice with that. All right, so this function that we have for this series will be 1 over 1 plus x, but then that's all raised to the third power. All right, so let's see how we're going to do this. So I think the series that this looks most similar to is 1 over 1 minus x. So kind of like the problem I did a few problems ago, I'm going to start with something that looks similar to this, which is 1 over 1 minus x. And I'm going to keep modifying it until I get this. All right, now let's see here. Oh, sorry, this is homework 15, number 3. All right, so what I'm going to do is first I want to make sure that this is going to be 1 plus x instead, because I have a 1 plus x down there. So that I can change by doing minus negative x. But then that's just plus x. The impact in here is that I have negative x to the n. That's negative 1 to the n, x to the n. So if you ever change the sign of your x like this, then you also have negative 1 that comes in to the same power as your x's. All right, now what I'm going to do is I notice that the whole bottom is raised to a power. That kind of gives me the idea to differentiate, because if I'm effectively using the power rule on this 1 plus x here, that can give me some higher powers in the bottom. I'm going to start doing derivatives to have this happen. Let's see, I'm going to do the derivative of this. So it's negative 1 over 1 plus x squared. Meanwhile, over here, if I do the derivative here, I have n negative 1 to the n, x to the n minus 1. All right, now the problem is I only have a squared down there, but that can be solved by doing another derivative and doing another product rule. So, or sorry, not product rule, power rule. I'm going to do the derivative again. So I multiply by my negative second power, cancels out the negative I have before, and then now it's to the third power on the bottom. This is the sum from 0 to infinity. If I do another power rule over here, meanwhile, I bring the n minus 1 down, and then we have this. Now this is almost exactly what we want. Remember, our goal was to get a series for 1 over 1 plus x cubed. But the problem is we have 2 over 1 plus x cubed. That's a very easy problem to fix. All we need to do is divide both sides by 2. So get rid of that, put a 1, and then we have 1/2 right there. There we go. There's our series. And for those of you who like to do this the other way, where you change your bounds on your index, this index could also start at n equals 2. Because if you put n equals 0 in here, this will all be 0. And if you put n equals 1 in here, that will also all be 0. So you could technically start this at n equals 2, and that would be totally fine as well if you like.
I would just integrate it, bro.
Are we gonna have to know when to change the bounds?
I'll tell you by default, I'm not going to change the bounds on my summations. That's why I don't like to teach it that way, because then you have to remember, okay, when do I change the bounds on this? You just don't have to.
Okay.
All right.
I have a question for this problem, because I know it's similar to what we previously did, but could you also just like take the 1 and can you take the original function and just do 1 over 1 minus negative x cubed as well, and then build your power series from there? Or you would have to do the whole matching thing?
So the problem is so that's not wrong to do that, but the problem is your series wouldn't look like any of the series you would have below. So what you're saying to do is we could do 1/1 minus 1 minus x cubed, or sorry, 1 plus x cubed. You're saying just put this into the geometric series?
Yeah, like 1 minus negative x cubed, because it has to be 1 minus, it's 1/1 minus r, whatever.
Yeah, so we could, in theory, we could do that. And there's no reason to say that this equality isn't true. But the problem is that this isn't easily identifiable as any of the other series that it's also equal to. So this is correct, but it's not particularly useful. And in general, I discourage you from substituting in something that has more than maybe just an x and a constant. Like if there's some complicated looking thing in there that has multiple terms, I wouldn't choose to do that for a substitution.
Can you explain again how you went from 1/1 minus x to 1/1 plus x? I think I missed that.
Yeah, sure. So the step in between here, I'm substituting in negative x for this x. So I have 1/1 minus, and I'm putting a negative x in place of the x. So when I do that, I have the sum from 0 to infinity of negative x to the n. But then a negative to the n is like a -1 to the n, and that's where that comes from. And then we have negative x, that's going to be a plus. So that's where we get that from. All right.
If you did all the different times you took the derivative and then you like made it 1 minus negative x, would that be fine?
Wait, I'm sorry. Could you say that again?
Yeah. So
wait, I get what you're saying. Sorry to interrupt. Yeah, so you're saying do this stuff with this series and then substitute in negative x at the end? Yeah, absolutely. You could do that. That's a totally valid way to do it.
Okay, thank you.
All right. Back in time here. All right. So the next question comes from Abigail. Can we do number 6 from the 2016 practice exam? Absolutely.
Actually, that was similar to the 2019 one we just did. So can we do number 7 from 2016 instead?
Yeah, sure. That's fine.
Thank you.
All right. Let's see what that is. Number 7. Oh, this is a good one. Okay, yeah, this is honestly probably my favorite Calc 2 problem because it really gets you to understand how intervals of convergence work. Okay, so this is a doozy here. Let's see, this is fall 2016, number 7. Okay, so what they do is they give you this series, right? So they give you the sum from 0 to infinity of c sub n x minus 6 to the n. And they say, so this is our power series here, right? And they say it converges for x equals 2, but it's going to diverge if we plug in x equals -2. And then it's asking what can be said about the following series, whether they converge or diverge. All right, so here are the series that we need to look at. First one is the sum from 0 to infinity of just c to the n, no coefficient. Q is the sum from 0 to infinity cn, and then we have 4 to the n next to it. R is the same thing as the others, only we have -1 to the n and 6 to the n. And finally, S is going to be the same thing, but with -9. -1 to the n, 9 to the n. And we need to see which one of these converge or diverge, or perhaps we don't have enough information. Maybe we actually can't tell what's going to happen with some of these. All right, so let's draw a number line here. This is going to be by far the most helpful thing to solve this problem. Okay, now the center of a series is called the center for a reason. The center of the series is at the center of the interval of convergence. So the center of the series is 6, right? It's always minus whatever the center is. So I'm going to put that right in the center of my number line. 6 goes right there. Now, another thing to know about power series intervals of convergence is that they're symmetric. So if you can go 3 steps to the left in X and still be fine, then you can go 3 steps to the right as well. So let's take a look here. We know it converges for X equals 2. So we know it's going to be okay at least that far. Now, what's the distance between these? It looks like we have a distance of 4 in between these right here. So that means that if I can go 4 this way and be all right, then in theory, I can go out towards 10 and also be okay. Now, the endpoints here, that's up for debate. So remember, even if the left endpoint can work, the right one might not work. So we don't really know about that, but everything in here is okay, and everything in here is okay. So between 2 to 10, including 2 but not 10, those are for sure safe. So let's go back here and see what X values we need to get these. So this one, if we just have 1 to the n times this or no coefficient, that comes from X equals 7. What do we need to make this be to have 4 to the n? I think we need to have this be X equals 10. All right, what do we need to have this be to be -6? That's X equals 0. And then what do we need to have this be to be -9? That's X is -3. Okay, so we can immediately answer that this one is okay. So P is going to converge because it's in the safe zone here. It's definitely within the radius of convergence, which is at least 4. We know we extend out to this 2. Okay, now let's use the other piece of information here. We know that if we keep going, I guess I should draw this a little bigger. We know that if we keep going, we're eventually going to hit a bad point. We're going to hit a point where it diverges at -2. Okay, so if we go all the way out here, then that's for sure not going to work. Now, what could happen in theory is my radius of convergence could be up to 8. Like it could go all the way here, but then maybe it just doesn't include that as an endpoint. And if I went 8 the other way, that would be totally fine. So if I went all the way to say X is 14, I actually wouldn't know what's going to happen with that. But once I get to 8 out in this direction, then I start hitting things that diverge. Meaning that if I go any further than 8 out in any direction, then it's not even a matter of endpoints anymore. Then I'm definitely stepping into divergent territory. So anything to the left of -2 will diverge, and anything to the right of 14, is 8 in this direction, that will diverge. But everything else, everything in here and everything in here, this is all unknown. We don't have enough information to tell us what's going to happen in there. We would need to know if another X value converged or diverged in order to say anything about that. So yeah, so for 10 through 14 inclusive, and then between -2 and 2 non-inclusive, we actually don't know whether it's going to converge or not, because we would need more information in this. All right. Yeah, where am I getting these X values from? Well, I need to give, like say I want to get 4 to the n, right? So I subtract a number by 6 and I want it to be 4, well, that's going to be 10. 10 minus 6 to the n is 4 to the n. That is 0 minus 6 to the n is -6 to the n, and -3 minus 6 to the n is -9 to the n. That's where I'm getting these from. All right, anyways, let's go back here and fill in our answers now. So X equals 10. So it seems like that one might converge, because if we went 4 in the other way, 2 would work. But remember, 10 could just be an endpoint, right? Like in theory, this is what we know. We know for sure this is true, and then this is true, right? So maybe our radius only extends out 4, and it only extends out 4 this way, but it doesn't include that endpoint. So in theory, our radius of convergence could be 4 and include the 2 endpoint, but not the 10. We actually don't know for 10. So 10, or the Q series here, we don't know about that. X equals 0, where does that fall into? That also falls into this mystery zone here, in between our good data point, our bad data points. This is another one. We have absolutely no idea. Now, X equals -3, that goes out beyond where we already had a divergent point. Once we have one divergent point, if we go any farther, we're going to have whatever. That'd be out here in this zone. So this would diverge. So this is kind of like a good logical exercise to get you comfortable with intervals of convergence and radii of convergence. And remembering that the endpoints don't need to be symmetric. You can include one, but then potentially not include the other end. That's also something to keep in mind. So the sum of the story here is that P will converge. We don't know about these two, and then S will diverge here. Why is our x equals 0 instead of x equals 12? It's because I have -1 to the n times 6 to the n. So this is effectively -6 to the n. So if I put 0 in here, I'm going to get -6. Yeah, I'm plugging stuff into here to get it to match these. Like this is technically a 1 to the n, and this is 4 to the n, -6 to the n, -9 to the n. Is it okay if we solve this by plugging x into there and use the numbers that are raised to n on the number line? So you can actually do that. So I couldn't plug in 1, 4, -6, and -9. That would not necessarily give me the same thing. So you cannot do that. You need to know what actual x value you plug into here. So you cannot just use these numbers like that. All right. Let's see
I
here.
had a question about this one.
Yeah, what's up?
So, what additional information would you need in order to like solve the question marks on the like number line?
You would need to know if another point converged or diverged. So for example, like let's say x equals, I don't know, let's say x equals 0 converged. So let's say that was another piece of information we have. So we can put 0 here. That's for sure going to work. So that means that the distance from 6 to 0 is 6. So that means that we can go the other way and go out to 12. And at least up to that, that would be okay. But since it's an endpoint, we don't really know. 12 would still be in question, but then anything from 10 to 12 would be okay. So if we got this additional information where x is 0, then we could state definitively that, yes, this one would converge. But we would need even more data points to get the other ones. So it's just knowing whether more points converge or not.
Thank you.
All right, guys. I'm about out of time for now. I have a meeting in a little bit. But yeah, as always, feel free to shoot me an email if you have any questions that we didn't get to, and I'll try to respond as soon as I can. But otherwise, I also have office hours tomorrow during period 4, and you could also set up an appointment with me as well. So anyways, yeah, I will see you guys later, and best of luck on the exam tomorrow.
Thank you, Mr. Manley.
Yeah, no problem.
Professor Manley?
Yeah, what's up?
So
let me stop recording real quick.